All right, imagine this. You sit down at your computer, planning to work for maybe an hour. You open your browser, check a few things, watch a quick video, and maybe switch over to your code editor for a while. Then suddenly it's evening, and somehow half the day is gone. The interesting thing is that most people have absolutely no idea where their screen time is actually going. They think they're spending 1 hour on a browser, but in reality, it might be 3. They think they're only checking social media for a few minutes, but it ends up being much longer. So in this video, we're going to solve that problem by building our own screen time tracker completely in Python. By the end of this project, we'll have a desktop application that can detect which application is currently active on your computer, track how long you're using it, store that information inside a database, display everything inside a modern dashboard, generate charts, and even export reports to a CSV file. And the best part is that we're building everything from scratch step by step, so even if you're a beginner, you'll be able to follow along. So let's jump into VS Code and start building this thing. Now, whenever we start a Python project, the very first thing we need is access to the tools that our program is going to use. And in Python, we get access to those tools through something called modules. Think of a module like a toolbox. Instead of building every tool ourselves, we simply import the tools we need and start using them. So let's start with our imports. So first, we're going to import CustomTkinter as CTK. Now, if you've never seen CustomTkinter before, don't worry. This is a library we're going to use to build the entire graphical interface of our application. Without this library, our project would only run inside the terminal. But since we want buttons, labels, dashboards, and a modern-looking application, we need a graphical user interface library. And CustomTkinter does a great job of making Python desktop applications look much cleaner than traditional Tkinter. You'll also notice that I'm writing as CTK. What this does is create a shorter nickname, basically an alias name. Instead of typing CustomTkinter every single time, we can simply type CTK, which makes our code much easier to read. Next, let's import SQLite 3. Now, our tracker needs somewhere to store data, because imagine tracking application usage for an hour and then losing everything the moment the program closes. That wouldn't be very useful. So we're going to use SQLite, which is a lightweight database built directly into Python. It allows us to store information permanently on the user's computer. Next, I'm importing threading. Later in the project, our application will be doing multiple things at the same time. It will be running the interface, updating labels, tracking applications, and responding to button clicks. If all of that happens in a single thread, the interface can freeze. So we'll use threading to run our tracking system in the background while the user continues interacting with the application. Next, we import time. This module gives us access to timing-related functions. For example, when we want our tracker to check the active application every second, we'll use this module. Now let's import psutil. This is one of the most important modules in the entire project. This will allow Python to interact with running system processes. In simple words, it helps us figure out which applications are currently running on the computer. And since our entire project depends on knowing which application the user is using, this module is absolutely essential. Next, we import Win32 UI and import Win32 process. These two modules help us communicate directly with Windows. They're going to allow us to identify the currently active window on the screen. So if the user switches from Chrome to VS Code, these modules help us detect that change. Now let's import datetime. Whenever we save information into our database, we'll also want to save the date. This allows us to know when the activity happened. And the datetime module gives us easy access to the current date and time. Next, we import matplotlib. This library is used for data visualization. Once we've collected screen time data, we don't just want raw numbers. We want charts that are easy to understand. So later, we'll use matplotlib to generate a visual breakdown of application usage. After that, we import pandas. Pandas is one of the most popular data analysis libraries in Python. We're going to use it when exporting our tracked information into a CSV report. It makes working with tabular data incredibly simple. And finally, we import the message box from Tkinter. Message boxes are those small pop-up windows that display messages to the user. For example, if the user tries to generate a report without any tracking data, we can display a warning message instead of letting the application fail. Alright, so now that our imports are done, the next thing we need is a place to store all the screen time data that our application is going to collect. Because think about it for a second. Let's say our tracker runs for 2 hours and successfully records every application we use. If we don't save that information somewhere, the moment we close a program, everything disappears. And that's exactly why we're going to create a database. Now, don't let the word database scare you. For this project, you can think of a database as nothing more than a file that stores information in an organized way. And since we imported SQLite 3 earlier, creating a database is actually very simple. So let's write con equals SQLite3.connect and then pass tracker.db as parameter. Now let's break this line down because there's quite a bit happening here. First, we have the word con. Notice that I could have called this anything. I could have called it a database. I could have called it DB connection. I could have called it my database. But con is short for connection, and it's a very common naming convention that you'll see in Python projects. Now after that, we have the equal sign. And remember, whenever we use an equal sign in Python, we're taking the value on the right side and storing it inside the variable on the left side. So whatever this code returns is going to be stored inside con. Now let's look at the right side. We're writing SQLite3.connect, and this connect function is responsible for creating a connection between our Python program and a database. Think of it like opening a communication channel. Without that connection, Python can't send information to the database, and it can't read information from it either. Now inside the parentheses, we're passing tracker.db. This is simply the name of our database file. And here's something really cool. If a file called tracker.db already exists, SQLite will connect to it. But if it doesn't exist, SQLite automatically creates it for us. So after running this line, we either connect to an existing database or get a brand new one. Now that we have a connection, we need a way to send commands to the database. And for that, we're going to create something called a cursor. So let's write cursor equals con.cursor. Again, on the left side, we're creating a variable called cursor. Now, what exactly is a cursor? Think of the connection as a phone line to the database. The cursor is the person speaking through that phone. Whenever we want to create tables, insert data, update records, or retrieve information, we do it through the cursor. Now notice we're writing con.cursor. The dot here means we're accessing something that belongs to our connection object. In this case, we're calling the cursor method. This method creates a cursor object and returns it back to us. And we're storing that returned object inside the variable called cursor. So from this point forward, whenever we want to communicate with the database, we'll use this cursor variable. All right, now that we can communicate with the database, we need somewhere to store our data. And that's where tables come in. You can think of a table like an Excel spreadsheet. It has rows and columns. Each row stores information, and each column represents a specific type of data. So let's create a table. To do that, we're going to write cursor.execute. Now, before I write the SQL query, let's understand what this line does. Remember how I said the cursor is responsible for talking to the database? Well, the execute method is how we send commands to the database. Whatever command we place inside execute will be forwarded to SQLite, and then SQLite will perform that action. In our case, the action we want to perform is creating a table. So inside execute, we're going to write a SQL command. And that command starts with create table if not exists usage. So let's try to understand this. Create table tells SQLite that we want to create a new table. If not exists is a safety feature. Without it, every time we run our program, SQLite would try to create the table again and throw an error if the table already exists. So we're basically saying, create this table only if it doesn't already exist. And finally, usage. This is simply the name of our table. You can think of it as the name of a spreadsheet. Now, inside the parentheses, we define the columns that will exist inside this table. The first column is ID integer primary key auto increment. Let's break this down. ID is the column name. This column will uniquely identify every record in our database. Next, we have integer. This means the value stored in this column must be whole numbers. Then we have primary key. This means this value must be unique for every row. No two rows can have the same primary key value. And finally, we have auto increment. This tells SQLite every time a new row is inserted, automatically generate the next number. So the first record might get 1, the second gets 2, and the third gets 3. And we never have to manually manage those numbers ourselves. The next column is app name text. The column name is app name and the data type is text. Since application names like Chrome, VS Code, or Spotify or Words, we need a text data type to store them. After that, we have usage seconds integer. This column stores how many seconds an application has been used, and because seconds are numbers, we're using the integer data type again. And finally, we have date text. This column will store the date when the usage was recorded. We're storing it as text because dates can easily be represented as strings. Once the entire query is finished, SQLite knows exactly what structure our table should have. But there's one final thing we need to do. We need to save those changes. So let's write con.commit. Now think of commit as a save button. Up until this point, SQLite knows about our changes, but they haven't been permanently written yet. When we call commit, we're telling SQLite, okay, everything looks good. Save these changes to the database. And now our database is officially ready. We have a connection, we have a cursor, and we have a table waiting to store all of the screen time data that our application is going to collect. Right below our database section, let's create a new section for tracking. And the first thing I'm going to write is tracking equals false. Now let's think about why we need this. Eventually, our application is going to have a start tracking button and a stop tracking button. When the user clicks start tracking, we need some way of telling our program, hey, tracking is currently running. And when the user clicks stop tracking, we need some way of telling our program, stop monitoring applications. That's exactly what this variable is going to do. Notice that I'm setting it equal to false. False is one of Python's Boolean values. A Boolean can only be one of two things, true or false. Right now, our tracker isn't running, so false makes perfect sense. Later, when the user clicks the start button, we'll change this value to true, and our tracking system will use that value to decide whether it should continue running or stop. Next, let's create another variable, usage data, and set it equal to empty curly braces. Now, if you've never seen curly braces before, this is called a dictionary in Python. A dictionary stores information using key-value pairs. The application name becomes the key, and the number of seconds becomes the value. So throughout the project, every time we detect an application, we're going to update this dictionary. By the end of a session, it might look something like this, which means Chrome was used for 240 seconds, VS Code for 540 seconds, and Spotify for 120 seconds. This single variable is going to hold all of our tracking information while the program is running. Now, let's create one more variable, session seconds, and set it equal to 0. This variable is going to track the total duration of the current tracking session. Notice that I'm assigning the value 0. That's because when the user first launches the application, no time has been tracked yet. As the tracker runs, we'll keep increasing this value. Later, we'll use this variable to display the live timer inside the dashboard. All right, now before we start writing our tracking logic, we need to do something a little unusual. We're going to create a placeholder function. And the reason we're doing this is because the tracking code we're about to write will eventually need a function called updateDashboard. The problem is that we haven't built our dashboard yet. So if we call updateDashboard right now, Python will throw an error because that function doesn't exist. Instead of jumping ahead and building the dashboard early, we're going to create a temporary placeholder. So we create a function called updateDashboard. Notice the keyword def. Def stands for define. Whenever we want to create a function in Python, we start with the def keyword. After that comes the function name, in our case, updateDashboard. I chose this name because later this function will be responsible for updating everything shown on the dashboard. Things like total time, top applications, usage statistics, and other information will eventually be updated here. Now, after the function definition, let's simply write pass. Now, what exactly does pass do? Pass is a special Python keyword that basically means do nothing. It's often used when we want a function to exist, but we haven't written its logic yet. So right now, this function doesn't actually update anything. It's simply acting as a placeholder, and later in the project, we'll come back and replace it with the real implementation. This is actually a common development technique because it allows us to keep building other parts of the application without running into missing function errors. All right, now comes the really interesting part. We're finally going to teach our application how to figure out which program the user is currently using. Think about what happens when you switch between applications. Maybe you're using Chrome, then you switch to VS Code, then maybe Spotify. At any given moment, one application is sitting in the foreground. In other words, it's the active window. Our goal is to detect that active window and identify which application it belongs to. So let's create a function for that. So we create a function called getActiveApp. Again, we're using the def keyword because we're creating a function. And I've named this function getActiveApp because its entire job is to return the currently active application. Now, inside the function, the first thing I'm going to write is try. Now, beginners often get confused by try statements, so let's understand why we're using it. The code we're about to write interacts directly with Windows, and sometimes Windows might fail to return the information we want. Maybe the process disappears, maybe access is denied, maybe something unexpected happens. If an error occurs and we don't handle it, our entire program could crash. A try block lets us safely attempt some code. If everything works normally, Python continues normally. If something goes wrong, we'll handle it using an except block. So inside the try block, let's write hwnd equals win32GUI dot get foreground window. Now, this line asks Windows which window is currently active. The return value gets stored inside a variable called hwnd. Now, don't worry too much about the name. It's short for handle to window. You can think of it as a unique identifier that Windows assigns to a window. Next, let's write underscore, comma, PID equals win32 process.getWindowThreadProcessID. Now, this might look a little strange, so let's break it down. We're passing hwnd into the function. Remember, it identifies the active window. This function returns two values. Since we only care about the process ID, we're ignoring the first value by using an underscore. The second value gets stored inside PID. PID stands for process ID. Every running application on your computer has a unique process ID. Chrome has one, VS Code has one, Spotify has one. And that's exactly what we're extracting here. Now that we have the process ID, we can get more information about that process. So let's write process equals psutil.process and pass the PID as a parameter. This line creates a process object using the process ID we just obtained. Think of it as grabbing the actual application behind that process. And finally, we'll return the process.name. The name method returns the name of the executable file. So if Chrome is active, this might return chrome.exe. If VS Code is active, then code.exe. And because we're using return, that value gets sent back to whoever called the function. All right, now let's finish our error handling. We'll write except and then return unknown. If anything goes wrong inside the try block, instead of crashing the entire application, we'll simply return the word unknown. This makes our tracker much more reliable. And just like that, we've built the first truly exciting part of our project. Our program can now identify which application is currently active on the screen. All right, before we continue building the rest of the tracker, I want to make sure that this function is actually doing what we expect. Because think about it. Everything in this project depends on our ability to identify the currently active application. If this function doesn't work, then there's no point in building the tracking system, the dashboard, the charts, or anything else. So let's test it. Now, obviously, this function won't run by itself. We need to call it. So down at the bottom of the file, just for testing purposes, I'm going to write print getActiveApp. Remember, this is only temporary. We're using it to verify that our function is working correctly. Later, we'll remove it. Now, before I run the program, notice that I currently have Google Chrome open, and Chrome is the active window on my screen. So if everything is working correctly, Python should be able to detect that and return the Chrome process name. Let's run the program and just open Chrome to make it our active window. Now, if we check our output, then there it is. You can see that the output says chrome.exe, which means our function successfully detected that Chrome was the active application. That's actually pretty cool when you think about it. A few minutes ago, this project was just an empty Python file, and now it can already communicate with Windows and identify what application is currently being used. But let's not stop there. One successful result doesn't necessarily prove everything. Let's test another application. This time, I'm going to switch over to VS Code. Notice that VS Code is now the active window. Chrome is still open, but VS Code is the application currently sitting in the foreground. So let's run the program again. And this time, the output says code.exe, which is exactly what we wanted. That tells us our function isn't hard-coded to Chrome or any specific application. Instead, it's dynamically checking whichever window is currently active and returning the correct process name. From this point forward, we now have the ability to answer the most important question in our entire screen tracker. What application is the user currently using? Now that we've verified everything is working correctly, I'm going to remove this temporary print statement because we no longer need it. And in the next section, we're going to take this one step further. Instead of checking the active application only once every single second, we'll build a tracking loop that continuously monitors the user's activity every single second. Alright, so at this point, we have a function that can tell us which application is currently active. And that's great, but think about what happens when we call that function. It checks the active application one time, returns a result, and then it's done. For example, if Chrome is active right now, it returns Chrome. But what if 10 seconds later I switch to VS Code, or 20 seconds later I open Spotify? Our current code has no way of knowing that because it only performs a single check. What we really need is a system that keeps checking over and over again, almost like a security camera that's constantly monitoring activity. And that's exactly what we're going to build now. We're going to create a loop that runs continuously while tracking is enabled. So let's create another function, and we'll call it tracking loop. Again, notice the name here. I've intentionally chosen the name tracking loop because that's exactly what this function is responsible for. It's going to contain a loop, and that loop is going to handle all of our tracking. Now, the first thing I'm going to write inside the function is global tracking. Now, if you're new to Python, this line might look a little strange, so let's talk about why we need it. Remember earlier we created a variable called tracking equals false. That variable lives outside of our function. Variables created outside functions are called global variables. And normally, Python tries to keep function variables separate from global variables. But inside this function, we're going to be reading the value stored in tracking. So by writing global tracking, we're telling Python, hey, when I refer to tracking inside this function, I'm talking about the global tracking variable that already exists. Now let's create the loop itself. We'll write while tracking. This line is incredibly important. Let's understand exactly what's happening. The keyword while creates a loop, and a while loop continues running as long as its condition remains true. In our case, the condition is tracking. Remember that tracking is a Boolean variable. It can either be true or false. So if tracking is true, this loop continues running. If tracking becomes false, the loop immediately stops. This is exactly what we want. When the user clicks Start Tracking later, we'll set tracking to true. And when they click Stop Tracking, we'll set it back to false. That means this loop automatically starts and stops based on the user's actions. Now that we have a loop running, we need to know which application is active during each iteration. So inside the loop, let's write app equals getActiveApp. Now, remember what this function does. It checks Windows and returns the currently active application, maybe chrome.exe, maybe code.exe, or maybe spotify.exe. Whatever application is active at that moment gets returned and stored inside the variable called app. Now we know which application is active. The next question becomes, how do we keep track of how much time has been spent in that application? That's where our dictionary comes in. So let's write usageDataApp equals usageData.get app, 0 plus 1. Now, I know this line looks intimidating, but once you understand it, it's actually very clever. Let's break it down piece by piece. First, we have usageDataApp. Remember that usage data is our dictionary, and app contains the name of the current application. So if app contains chrome.exe, then this becomes usage data chrome.exe, which represents Chrome's stored usage time. Now look at the right side, usagedata.get app, 0. The get method is used to safely retrieve a value from a dictionary. The first argument is the key we want, in this case app, and the second argument is the default value, which in this case is 0. So if Chrome already exists inside the dictionary, Python simply returns its current usage time. Maybe 120 seconds, maybe 300 seconds, whatever value is already stored. But if Chrome doesn't exist yet, instead of throwing an error, Python simply returns 0. Now look at the final part, plus 1. Since our loop runs once every second, we're essentially saying, take the current value and add one more second.
So if Chrome previously had 120, then it becomes 121, then 122, then 123, and so on. This single line is what allows our tracker to accumulate usage time over the entire session. Now that we've updated the data, the next thing we want to do is refresh our dashboard. Eventually, we'll display all this information inside the user interface. So let's call our update dashboard function here. Right now, our dashboard function doesn't actually do anything. Remember, it's still a placeholder, but that's perfectly fine. We're building the project in stages. Later, we'll replace that placeholder with real dashboard logic. For now, we just want this function call to exist, so our tracking loop is already prepared for the future dashboard. And finally, let's slow the loop down a little bit, because if we don't, Python will run this loop thousands of times every second, and that's definitely not what we want. So let's write time.sleep and pass 1 as a parameter. Now, the sleep function comes from the time module we imported earlier. The number inside the parentheses represents seconds, so time.sleep1 means pause execution for 1 second. This creates a nice predictable rhythm. Check active application, update usage, wait 1 second, check again, update usage, wait 1 second, and repeat. And just like that, we've built the core engine of our entire screen time tracker. Everything else in this project, charts, reports, dashboards, analytics, depends on the data collected by this loop. This is the part that's actually watching what applications are being used and recording that information over time.
All right, so at this point, our tracking loop is capable of collecting usage information and storing it inside the usage data dictionary. But there's a small problem. Actually, it's a pretty big problem. Everything we're tracking currently exists only in memory, and memory is temporary. The moment we close the application, all of that information disappears. So if someone spends 3 hours using their computer and then closes the tracker, we lose all of that data. Obviously, that's not what we want. Instead, we want to save that information inside the database we created earlier. That way the data remains available even after the program closes. So let's create a function that handles that job. So we'll create a function called SaveToDatabase. Just like before, we're using the def keyword because we're creating a new function. And I've chosen the name SaveToDatabase because I want the function name to clearly describe what it's doing. Whenever another developer reads this code, or even when you come back to this project months later, you should immediately understand its purpose. Now, the first thing we need is today's date, because every usage record should be associated with a specific day. Otherwise, if someone tracks usage today and then again tomorrow, we won't know which record belongs to which day. So let's write today equal datetime.now strftime. Now I know this line looks a little intimidating, so let's break it down carefully. First, we have datetime.now. Remember that earlier we imported datetime. The now method returns the current date and time. For example, it might return something like this, which contains year, month, day, hour, minute, and second. Now after that, we're calling .strftime. The name stands for string format time, and its job is to convert the date into a string format that we choose. Inside the parentheses, we're passing %y, %m, and %d. Let's understand what each part means. %y represents the 4-digit year, for example, 2026, and %m represents the month, and %d represents the day. Now that we have the date, we need to save each application's usage information. Remember, all of our track data currently lives inside the usage data dictionary, so we need a way to go through every item inside that dictionary, and for that, we'll use a loop. Let's write for app, seconds in usagedata.items. Now let's slow down and understand what's happening here. The items method returns both the key and the value from a dictionary. And remember what our dictionary looks like, something like this. In this case, the app receives the key and seconds receives the value. So during the first iteration, app becomes chrome.exe and seconds becomes 300. And during the next iteration, app becomes code.exe and seconds becomes 500. This allows us to process every tracked application one by one. Now that we have the application name and usage time, we can finally insert that information into the database. So let's write cursor.execute. Remember earlier when we created the table?
I mentioned that the execute method is used to send commands to SQLite. That's exactly what we're doing again. This time, instead of creating a table, we're inserting data. So inside execute, we're going to write insert into usage. The words insert into tell SQLite we want to add a new row into a table. And the table we're inserting into is usage, which is the table we created earlier. Now underneath that, we're writing app name, usage seconds, and date. These are the specific columns that will receive data. And notice that these names exactly match the column names we defined when creating the table. That's important because SQLite needs to know where each value should go. Next, we're writing values and pass 3 question marks. Now, beginners often wonder why we use question marks here. The reason is that these are placeholders. Think of them like empty slots. We're telling SQLite, don't worry about the actual values yet, we'll provide them separately. And that's exactly what happens in the next line. We're passing app, seconds, and today. Now let's connect everything together. The first question mark receives app. The second receives seconds, and the third receives today. So if Chrome was used for 300 seconds, SQLite might receive something like chrome.exe, 300, and the date. And it inserts that information as a new row inside the database. The loop then repeats for every application stored inside the dictionary. So by the time the loop finishes, all tracked applications have been saved. And just like that, we've connected our tracking system to persistent storage. Now our application doesn't just collect screen time data, it can actually save that data for future use. All right, so at this point, we've built quite a bit of functionality. We have a database, we can detect active applications, we have a tracking loop, and we even have a function capable of saving usage information. But if I gave this program to someone right now, they wouldn't know how to use it. Why? Because there's no interface. Everything exists behind the scenes. So now let's start building the graphical interface that users will actually interact with. And since we imported CustomTkinter earlier, we're going to use it to create a modern desktop application. The very first thing I'm going to write is ctk.setAppearanceMode and pass light as the argument. Let's understand what this line does. CustomTkinter supports different appearance modes, for example, light mode, dark mode, and system mode where it follows the operating system's theme. In our case, I'm choosing light mode because I want a clean dashboard style appearance. So whenever the application launches, it will use a light color scheme. Next, let's write ctk.setDefaultColorTheme and pass blue as the argument. Now this line controls the default accent color used by CustomTkinter. Things like buttons, switches, sliders, and other interactive components will use this theme color. Now it's finally time to create the application itself. So let's write app equals ctk.ctk. This line is extremely important. Think of it as creating the main window of our application. Without this line, we wouldn't actually have a window to display. Notice that I'm storing it inside a variable called app. This variable now represents our entire application window. Any widgets we create later will be attached to this app object. Now let's set the size of the window. We'll write app.geometry and pass 1100 by 750 in it. Now the geometry method controls the window dimensions. Inside the quotation marks, we're providing width times height. So 1100 represents the width and 750 represents the height. This gives us plenty of space for dashboard information later. Now let's give the window a title. We'll write app.title and then write screen time tracker. Whenever the application launches, this text will appear at the top of the window. It helps users immediately understand what the application is. Next, let's write app.configure and then pass fgcolor. The configure method allows us to modify the properties of a widget. And remember, our application window is also a widget. The property we're changing here is fgcolor, which stands for foreground color. This controls the main background color of the application. Now you might be wondering, what is this strange value? This is called a hexadecimal color code. It's simply another way of representing colors. This particular color is a very soft, light gray. At this point, we officially have an application window, but if we run it right now, the window will appear and then immediately disappear. And the reason is simple. Python reaches the end of the file and exits, so we need a way to keep the application running, and that's where the next line comes in. Let's write app.mainLoop. This line starts the application's event loop. Now, don't worry too much about the word event loop. For now, you can think of it as the engine that keeps the interface alive. Without the main loop, the window would open and instantly close. With the main loop, the application remains open and waits for things like button clicks, keyboard input, mouse actions, and other user interactions. And just like that, we officially have the first version of our application window. It doesn't have any buttons yet, it doesn't have any labels, and it definitely hasn't built a dashboard. At this stage, our goal is much simpler. I just want to make sure our application window is being created correctly. So let's run the program and see what we've built so far. Now, don't expect anything fancy yet. We haven't created buttons, we haven't created labels, and we definitely haven't built a dashboard. At this stage, our goal is much simpler. I just want to make sure our application window is being created correctly. So let's run the program and see what we've built so far. And there it is. Notice that we now have an actual desktop application. You can see the title at the top, you can see the window size we specified, and you can also see that soft gray background color we configured a moment ago. Now, obviously, it looks pretty empty right now, and that's completely expected. Think of this like constructing a house. We've just built the foundation and the outer structure. The furniture, decorations, and everything else will come later. But this is still a huge milestone because we've officially moved from back-end logic to a real graphical application. All right, let's start filling this window with actual dashboard components. All right, now that we have an application window, let's start adding some actual content to it. And the first thing I want users to see when they open the application is a title. Because the moment someone launches this program, they should immediately understand what they're looking at. So let's create a label. We'll write title equals ctk.ctk label. Now, if you've never worked with GUI libraries before, a label is simply a widget used to display text. Think about things like headings, titles, captions, and status messages. All of those are typically displayed using labels. Now, notice that the first thing we're passing is app. This is important. Remember earlier when we created app equals ctk.ctk? That app variable represents our main application window. By passing app here, we're telling CustomTkinter, place this label inside the application window. Now let's add some text. We'll write text equals screen time dashboard. This is the text that users will actually see. Next, let's make it larger. We'll write font equals Arial, 36, bold. Now this parameter controls how the text looks. Inside the parentheses, we have three values. The first value, Arial, is the font family. The second value, 36, is the font size. And the third value, bold, controls the font style. So this will create a large, bold heading that's easy to notice. Next, let's define a text color. We'll write text color equals hexadecimal color. Again, we're using a hexadecimal color code. This particular color is a dark gray. Now, after creating the label, we need to display it. So let's write title.pack and pass pad y equal to 25. Now let's talk about pack. Creating a widget does not automatically display it. We need a layout manager, and pack is one of the layout managers available in Tinker. Its job is to place widgets inside the window. Now notice we're also passing pad y equal to 25. The word pad y stands for vertical padding. In other words, we're creating some empty space above and below the label. Without padding, everything would look cramped together. So this helps make the interface cleaner. All right, now directly underneath the title, I want to show the current status of the tracker. For example, ready, tracking running, tracking stopped. These messages help users understand what's happening. So let's create another label. We'll write status label equals ctk.ctk label. Again, we're creating a label, and once again, we're attaching it to our app window. For the text, we'll write text equals ready. Why ready? Because when the application first launches, tracking hasn't started yet, so ready is a good default state. Now for the font, we set the font to Arial, font size to 20, and style to bold. Next, we'll choose another text color. And finally, status label.pack. At this point, users will see ready right underneath the dashboard heading. Now let's create something even more interesting, a live timer. Think about applications like stopwatches, timers, and fitness trackers. They all give users immediate visual feedback, and that's exactly what we want. When someone clicks Start Tracking later, they'll instantly see time increasing on the screen. So let's create another label. We'll write timer label equals to ctk.ctk label. Again, we're attaching it to our app window. Now for the text, we write text equals 00:00:00. This represents hours, minutes, and seconds. Since tracking hasn't started yet, everything begins at 0. Now let's make this timer much larger. So we will set the font to Consolis and font size to 42 and make it bold. Next, let's choose a color. So we set the text color to bright orange color. Finally, let's display it. Timerlabel.pack and set the pad Y equal to 10. Again, we're adding some vertical spacing to keep the layout clean. And just like that, we've created the first real dashboard components. We now have a dashboard heading, a status indicator, and a live timer display. And even though the timer isn't moving yet, the structure is already in place. Later in the project, when we build the Start Tracking functionality, we'll connect real data to these labels and bring the dashboard to life. All right, let's run the application and see how it's starting to come together. And immediately, you can see a huge difference compared to before. Earlier, we just had an empty window. Now we actually have structure. At the top, we have the Screen Time dashboard heading. Directly underneath that, we have a status label showing ready. And below that, we have our timer display initialized to 0. Now, the timer isn't moving yet, and that's completely expected because we haven't connected any tracking functionality to it. Right now, we're focused on building the interface first, then connecting the functionality afterwards. This is actually a common development approach. First, create the visual components, then connect them to real data. But even at this stage, the application already looks much closer to a real dashboard than an empty window. Now, we're going to make things even more interesting by adding our control buttons so users can actually interact with the tracker. All right, so now that our dashboard has a title, a status indicator, and a timer display, the next thing we need is a way for users to interact with the application. Because eventually, users need to be able to start tracking, stop tracking, view analytics, and export reports. And all of those actions are going to happen through buttons. But before we create the buttons themselves, I want to create a dedicated area that will hold them. This helps keep our interface organized. So let's start by creating a frame. We'll write button frame equal to ctk.ctk_frame. Now, if you've never used a frame before, think of it as a container. A frame doesn't really do anything by itself. Its purpose is simply to hold other widgets. In our case, it's going to hold all of our buttons. Just like a folder helps organize files, a frame helps organize widgets. Now, the first thing we're passing is app, which means this frame will be placed inside our main application window. Next, we set foreground color to white. Remember earlier when we customized the background color of the application? We're doing something similar here. This time, we're setting the background color of the frame itself, and this hexadecimal value represents pure white. Next, let's write corner radius equal to 15. Now, this is one of the nice things about CustomTkinter. Traditional Tkinter widgets often look very square and dated. The corner radius property allows us to create rounded corners. The larger the number, the more rounded the corners become. A value of 15 gives us a modern dashboard-style appearance. At this point, we've created the frame. But remember, creating a widget does not automatically display it. So let's place it on the screen. So we'll write buttonframe.pack and set the pad Y to 25. Again, we're using the pack layout manager. And this time, we're adding vertical spacing around the frame. This helps separate it from the timer above. Now that our container exists, let's start creating buttons. And the first button we'll create is the most important one, the Start Tracking button. So let's write start btn equal to ctk.ctk button. Now this will create a button widget. And notice something important. The first parameter is not app, it's a button frame. This tells CTK, place this button inside the frame, not directly inside the application window. This is what keeps our layout organized. Now let's define the text. We'll write text equal start tracking. This is what users will see displayed on the button. Next, let's define a width. We'll write width equal 180. This controls how wide the button appears. Then height equals 45, which controls the button height. Giving buttons consistent dimensions helps the interface look professional. Now let's define the font. We'll set the font family to Arial, font weight to 16, and make it bold. By now, this should look familiar. We're simply controlling how the text appears. And finally, command equal start tracking. Now, this is probably the most important property of the entire button. The command parameter tells Python what should happen when the button is clicked. Notice that I'm writing start tracking without parentheses. This is very important. If I wrote start tracking with parentheses, Python would immediately execute the function while the application launches. But that's not what we want. Instead, we're giving Python a reference to the function. We're basically saying, when the user clicks this button later, call this function. Now, don't worry if the function doesn't exist yet. We'll create it later. For now, we're simply preparing the interface. Now let's display the button. We'll write startbtn.grid. Now, you might notice something interesting. Earlier, we used pack, but now we're using grid. Why? Because inside the frame, we want precise positioning. The grid layout system allows us to arrange widgets using rows and columns. Think of it like a spreadsheet. We're placing this button at row 0 and column 0, which means first row, first column. Then we add pad x equal to 12 for horizontal spacing and pad y to 15 for vertical spacing. This helps prevent buttons from touching each other. Now that we've created one button, the remaining buttons follow exactly the same pattern. The next button is stop tracking. This will eventually stop our tracking loop. Then we'll create View Chart, which will allow users to see a visual breakdown of application usage. And finally, Export CSV, which will save usage data into a CSV report. Notice that all of these buttons use the same width, height, and font settings. Keeping those values consistent helps create a clean, professional interface. The only things changing are the button text, the command function, and the column position inside the grid. And just like that, our dashboard now has a complete control panel. Users can see exactly which actions are available and where those actions will eventually happen. Right now, I'm creating temporary placeholder versions of these functions because the button needs something to connect to. Later in the project, we'll come back and build the actual functionality. All right, let's run the application again. And now you can really start seeing the dashboard come together. We still have our title, we still have our status label, we still have our timer, but now we also have a complete control panel. You can see a Start Tracking button, a Stop Tracking button, a View Chart button, and an Export CSV button. Now, if I click them right now, nothing happens. And that's actually expected. Remember, these buttons are currently connected to placeholder functions. We haven't written the real functionality yet. At the moment, our goal is simply to build the interface structure. Later, we'll come back and teach each button exactly what it should do. But visually, the application is already starting to look like a real screen time tracker.
All right, so our Start Tracking button now exists. Users can see it, they can click it, but at the moment, it doesn't actually do anything. That's because the function connected to it is still just the placeholder. So let's fix that. We're going to replace the placeholder with the real implementation. So first, we will create a function called Start Tracking. By now, function definitions should feel familiar. This function is going to run whenever the user clicks the Start Tracking button. Now, the first thing I want to do is access a couple of global variables. So let's write global tracking and global session seconds. Let's talk about why we need these. Earlier, we created tracking equal false and session seconds equals 0 outside of any function. That means they're global variables. And since this function needs to work with those variables, we're telling Python, use the global versions that already exist. Now, the next thing I'm going to write is if tracking, then simply return. This is a small piece of code, but it's actually very important. Imagine the user clicks Start Tracking, and then tracking begins. Then they accidentally click Start Tracking again, and again, and again. Without protection, we could accidentally create multiple tracking threads running at the same time. That would cause all kinds of problems. So this condition acts like a safety check. If tracking is already running, we simply exit the function immediately. Nothing else happens. This prevents duplicate tracking sessions. Now let's reset the session timer. We'll write session seconds equals 0. Remember what this variable represents? It's the amount of time tracked during the current session. Whenever the user starts a brand new session, we want the timer to begin from 0. So we're resetting it here. Next, let's actually start tracking. We'll write tracking equal true. This line is extremely important. Remember our tracking loop?
Earlier, we wrote while tracking. That loop only runs when tracking is true. So by changing this value, we're effectively giving the tracking loop permission to start running. Now let's update the status label. We'll write statuslabel.configure and then set the text equal to tracking running. Let's break this down. The configure method is used to modify a widget after it has already been created. In this case, we're modifying the status label. Originally, the label displayed ready, but now tracking has started, so we want the interface to reflect that. So the new text becomes tracking running. This gives users immediate feedback that something has changed. Now let's call update live timer. At the moment, we haven't built this function yet, and that's okay. Just like before, we're building things step by step. For now, you can think of this function as the thing that will eventually keep updating the timer shown on the dashboard. We'll create it shortly. Now comes one of the most interesting parts of the entire project. Let's write thread equals threading.thread. Remember earlier when we imported threading? This is where we finally use it. Now let's add our first parameter. Target equals tracking loop. The target parameter tells Python what function should this thread run. In our case, we want it to run tracking loop, which is the function we built earlier. Now let's add daemon equals true. This tells Python if the main application closes, automatically stop this thread too. Without this, background threads can sometimes continue running after the application exits. So setting daemon equal to true makes our program cleaner and safer. Now that the thread has been created, we need to start it. So let's write thread.start. Creating a thread and starting a thread are two different things. Think of creating a thread like building a car. The car exists, but it isn't moving yet. When we call thread.start, that's the equivalent of turning the key and starting the engine. At that moment, Python launches a new thread and begins running our tracking loop in the background. And that's exactly what we want, because now our application can do two things simultaneously. The interface remains responsive, and the tracking engine continues monitoring applications in the background. Without threads, the interface would freeze while tracking was running, and that's definitely not the experience we want. And just like that, our Start Tracking button officially has real functionality. When the user clicks it, the status updates, the timer begins, and the tracking engine starts running in the background. All right, let's run the application and see what happens. Now remember, we haven't built the timer functionality yet, and we also haven't finished the stop tracking button. So don't expect the full application to work. What we're testing right now is only the start tracking functionality. So I'm going to click Start Tracking, and immediately notice what changed. The status label switched from ready to tracking running. That's exactly what we wanted. The button is now successfully communicating with our application and triggering real functionality. Now behind the scenes, our tracking thread has also started running. We can't see that happening yet because we haven't built the dashboard updates, but the tracking engine is officially active. Next, we're going to bring the timer to life so users can actually see tracking progress happening in real time. All right, so at this point, our Start Tracking button is working. When the user clicks it, the status changes to tracking running, and our tracking thread starts running in the background. But there's still something missing. Right now, the user has no visual indication that time is actually being tracked. So let's fix that by building a live timer. The goal is simple. Every second, we want the timer displayed on the screen to update itself. So let's create a function. We'll create an updated live timer function. Now remember, this function is going to be responsible for updating the timer label over and over again. And since it will run repeatedly, we need to be careful about when it should update and when it should stop. The first thing I'm going to write is if tracking. Now let's think about why this condition matters. Remember, earlier we created tracking equals false. And when the Start Tracking button is pressed, we change it to tracking equals true. So this condition is essentially asking, is tracking currently running? If the answer is yes, then we'll update the timer. If the answer is no, we'll simply stop. This prevents the timer from continuing after tracking has been stopped. Now inside the condition, we need access to our session timer variable. So let's write global session seconds. Remember, session seconds was created outside the function, and because we're going to modify it, we need to tell Python that we're working with the global version. Now let's increase the timer. We'll write session seconds plus equal to 1. Now, if you've never seen this syntax before, let's break it down. This is simply shorthand for session seconds equal to session seconds plus 1. In other words, take the current value, add 1, and store the result back. So if the value was 0, it becomes 1, then 2, then 3, and so on. Since this function runs every second, session seconds will accurately track the duration of the current session. Now that we know how many seconds have passed, we need to convert those seconds into something more user-friendly, because showing something like 3785 seconds isn't nearly as useful as showing 1 hour, 3 minutes, and 5 seconds. So let's calculate hours first. We'll write hours equals session seconds, then /3600. Now let's understand where 3600 comes from. There are 60 seconds in a minute and 60 minutes in an hour. So 60 multiplied by 60 equals 3600 seconds. The // operator performs integer division. Next, let's calculate minutes. We'll write minutes equal session seconds percent 3600 and then / and 60. I know this looks a little complicated, so let's break it down carefully. The percent symbol is called the modulus operator. It returns the remainder, so session seconds modulus 3600 gives us whatever seconds are left after removing complete hours. And then we divide by 60 to determine how many full minutes remain. And finally, let's calculate seconds. We'll write seconds equal session seconds modulus 60. Again, we're using modulus. This time, we're finding the remaining seconds after removing complete minutes. At this point, we have hours, minutes, and seconds stored separately. Now, let's update the timer label. We'll write timerLabel.configure. Just like we used to configure earlier for the status label, we're now using it to modify the timer label. Specifically, we're updating the text. So let's write text equals fstring and then hours:02, minutes:02, and seconds:02. Now this is something called an fstring. An fstring allows us to insert variables directly into text, but notice the :2. This formatting instruction tells Python always display at least 2 digits, so 5 becomes 05 and 9 becomes 09. This helps our timer maintain a professional clock-like appearance. Without it, our timer might look like this, which isn't nearly as clean. Now we've updated the timer, but there's one final challenge. How do we make this function run again after 1 second? If we don't do anything, the function runs once and then stops, and that's not what we want. We want continuous updates. So let's write app.after, and then we pass 1000, and update live timer. This line is one of the most important lines in the entire timer system. The after method tells tkinter, wait a certain amount of time and then run a function. So the first argument is 1000, which represents milliseconds. And since there are 1000 milliseconds in 1 second, we're saying wait 1 second. The second argument is update live timer, which is the function we want to run again. Notice that we're not writing parentheses. Just like button commands, we're providing a function reference. So here's what happens. The timer updates, then tkinter waits 1 second, then this function runs again. Then it waits another second, then it runs again, and that cycle continues for as long as tracking remains active. And just like that, we've created a self-updating live timer. Every second, the session counter increases, the display refreshes, and the user gets immediate visual confirmation that tracking is happening. All right, let's test this. Now remember, we already connected our Start Tracking button to the Update Live Timer function in the previous section. So if everything is working correctly, the moment I click Start Tracking, the timer should begin counting upward. Let's run the application. And now I'm going to click Start Tracking. Notice what happens. The status changes to Tracking Running, and now the timer starts increasing every second. This is exactly what we wanted. Now, from a user's perspective, there's no longer any doubt about whether tracking is active. The timer provides immediate feedback that the application is currently monitoring activity. And honestly, this is one of those moments where the project starts feeling real, because we're no longer just creating interface components. We're creating components that respond to user actions and update themselves dynamically. Now we'll build the stop tracking functionality so users can properly end the tracking session and save their data.
All right, so now that users can start a tracking session, the next thing we need is a way to end it. Because imagine someone starts tracking in the morning. They work for a few hours, and then they want to stop the session and save the results. Without a stop tracking feature, the tracker would just keep running indefinitely. So let's build that functionality now.
We'll start by creating a function. So we will create a function called stopTracking. Just like the start tracking function, this function will run whenever the user clicks the Stop Tracking button. Now, the first thing we need is access to our tracking variable. So let's write global tracking. Remember, tracking is the variable that controls our tracking loop. Earlier, we wrote while tracking, which means the loop only continues while tracking is true. So if we want the loop to stop, we need to change that value. And that's exactly what we're going to do. So let's write tracking equal false. This line is very important. The moment this executes, the condition inside our tracking loop becomes false, and because of that, the loop exits. In other words, this single line is what tells our tracking engine to stop monitoring applications. Now that tracking has stopped, we also want the timer display to reset because the session is over. So let's write timerLabel.configure, and inside that we'll update the text. Remember, configure allows us to modify an existing widget? In this case, we're updating the timer label. So after the session ends, the timer immediately returns to 0. This prepares the dashboard for the next tracking session. Now, here's where things get really interesting. Up until this point, all of our tracked data has been sitting inside the usage data dictionary. The data exists, but it only exists in memory. If the application closed right now, we'd lose everything. So before finishing the session, we need to save that information. And thankfully, we already built a function for that. So let's call our save to database function. Remember earlier when we spent time creating this function? This is the moment where it finally gets used. The function will retrieve today's date, loop through all tracked applications, insert records into the database, and commit the changes. So with a single function call, all collected usage information becomes permanently stored, and that's exactly what we want. Now that the session has ended, let's update the status label. We'll write status label configure and then text equal to tracking stopped. Just like we changed the status to tracking running when the user started tracking, we now want to inform them that tracking has ended. This provides immediate visual feedback and helps users understand the current state of the application. And that's it. The stop tracking function is actually much simpler than the start tracking function, but it's doing some very important work. It stops the tracking loop, it resets the timer display, it saves usage information, and it updates the dashboard. All of those actions happen with just a few lines of code, and together they complete the entire tracking cycle. Users can now start tracking, collect usage data, and stop tracking while saving everything to the database. All right, let's test this out. I'm going to start by clicking Start Tracking. You can see the status change to tracking running. The timer begins increasing and everything looks exactly as expected. Now let's pretend we've been tracking for a while and we're ready to end the session. I'm going to click Stop Tracking and immediately notice what happens. The timer resets back to 0, the status changes from tracking running to tracking stopped, and behind the scenes, our usage data has also been saved to the database. What's really nice here is that a single button click is triggering multiple actions. We're stopping the tracking loop, updating the interface, and saving data all at the same time. And that's exactly how a real application should behave. At this point, our tracker is already functional. We can start tracking, we can stop tracking, and we can save usage information. But there's still one big problem. The user can't actually see any of the data we've collected. Right now, it's hidden inside a dictionary and inside a database. So now we're finally going to build the dashboard components that display usage information directly inside the application. All right, so before we can display any usage information, we need somewhere to display it. Think about it. Even if our tracking system calculates everything correctly, the user still needs a place to see those results. So let's create the dashboard components that will hold that information. The first thing I want to display is the total amount of tracked time, because that's usually the first thing users want to know. How much time have I spent on my computer during this session? So let's create another label. We'll write total label equals ctk.ctk_label. Just like before, we're creating a label widget, and since we want this label to appear inside the main application window, the first argument is app. Now let's define the initial text. we'll write text equals total time colon 0 minutes. Now, obviously, this isn't the real value. The real value will be calculated dynamically later, but when the application first launches, no tracking has happened yet, so showing 0 makes perfect sense. Next, let's define the font. We'll set the font family to Arial, font size to 26, and make it bold. Next, let's define the text color. So we'll set the text color to dark gray color. Now let's display the label. We'll write totallabel.pack and set the pad y to 20. The pack method places the label on the screen, and the vertical padding gives it some breathing room. All right, now that we have a place for the total time, we need a place to display application usage details. For example, Chrome, VS Code, Spotify, and how long each application has been used. So let's create another label. We'll write appbox equals ctk.ctk label. Now you might be wondering, why are we using a label instead of something like a table? The answer is simplicity. For a beginner project, a label is more than enough, and it allows us to focus on the tracking logic rather than advanced UI widgets. Now again, the first argument is app, because this widget belongs inside our application window. Now let's define the initial text. We'll write text equals to no data yet. This is what users will see before any tracking has occurred. It's a simple way of indicating that no information is currently available. Now let's define the width. We'll write width equals to 850. This controls how wide the widget appears. And then we write height 400, which controls the vertical size. We're intentionally making this widget fairly large because it will eventually display multiple applications and their usage times. Now let's give it rounded corners. We'll write corner radius equals 20. Again, this helps create a modern dashboard appearance. Next, let's define the background color. We'll set the background color to white, and then we set the text color, and then we set anchor equal to NW. Now this parameter is extremely important. The anchor controls where the text begins. The letters N and W stand for north and west. In other words, top left. So this tells CustomTkinter, start displaying text from the top left corner. Without this, the text would appear centered, which wouldn't work very well for a usage list. Then we set the justify to left. This ensures multiple lines of text remain left aligned. Again, that's exactly what we want for a usage report. Now let's define the font. We'll set the font family to Consolis and the font size to 20. And finally, we write appbox.pack and set the pad y to 25, which places the widget onto the dashboard. And just like that, we've created the visual components that will eventually display our tracking data. Right now, they aren't connected to anything. They're simply placeholders waiting for real information. But that's exactly how interface development often works. First, we create the display elements, then we connect them to the underlying data. And that's exactly what we're going to do next. All right, let's run the application again and see how the dashboard is evolving. And now you can really start seeing the structure of the final project. We still have our title, we still have our timer, we still have our control buttons, but now we also have dedicated sections for displaying usage information. You can see a total time area, and underneath that, a large usage panel that currently says no data yet. Now, obviously, there's no real data showing up yet, and that's completely expected. The tracking system is collecting information, but we haven't connected the dashboard to that data yet. Right now, we're building the display components first. Now we're going to connect these components to our tracking data, and finally bring the dashboard to life. That's the point where application names and usage times will start appearing automatically.
All right, it's finally time to bring our dashboard to life. Up until now, every time our tracking loop ran, it was calling update dashboard. But that function wasn't actually doing anything. It was just a placeholder. Now we're going to replace it with the real implementation. So first, I'm going to create an update dashboard function. Now this function will be responsible for refreshing everything displayed inside the dashboard. Whenever tracking data changes, we'll call this function so the interface always stays up to date. Now the first thing we need to know is how much total time has been tracked so far. Remember, all of our application usage information is stored inside the usage data dictionary, something like this. Each value represents seconds, so if we want the total tracked time, we simply need to add all those values together. So let's write total time equals sum and then pass usage data.values. Now let's break this down.
First, we have UsageData.values. The values method returns all the values stored inside the dictionary. So if our dictionary looked like this, then the values would return 120 and 300. Now we're passing those values into sum function. The sum function adds everything together, so 120 plus 300 becomes 420, and that result gets stored inside the total time variable. At this point, total time contains the total number of tracked seconds across all applications. Now we need to convert those seconds into something more user-friendly, because users don't want to see 420 seconds as output. They want to see it in the form of hours and minutes. So let's calculate the hours first. We'll write hours equal total time and then / 3600. Remember, from the timer section, 3600 seconds equals 1 hour, and integer division tells us how many complete hours fit inside the total. Next, let's calculate minutes. So we'll write minutes equal total time modulus 3600 integer division by 60. Again, we're using modulus to remove complete hours first. Then we're dividing by 60 to determine the remaining minutes. And finally, seconds equal total time modulus 60. This gives us whatever seconds remain after removing complete minutes. At this point, we now have hours, minutes, and seconds stored separately. Now let's update the total label. We'll write total label.configure. Remember, configure allows us to modify an existing widget. We're specifically updating the text property. So let's write text equal fstring total time, and then hours, minutes, and seconds. By now, the formatting should be familiar. The :02 ensures that every value uses 2 digits. So instead of showing like this, we get the output in this form, which looks much cleaner. Now the total time section is finished, but that's only part of our dashboard. We also want to display information about individual applications. So let's create a sorted version of our dictionary. We'll write sorted apps equal sorted. Now, if you've never used sorted before, it simply takes data and returns a sorted version. In our case, we want the most used applications to appear first. So inside the sorted function, we're writing UsageData.items. Remember, items return both keys and values. Now, let's define how the sorting should work. So we'll write key equal lambda x:x and then 1. This line often scares beginners, but it's actually much simpler than it looks. Think of it as telling Python, when sorting, use the second value. Remember, x0 would be the application name and x1 would be the usage time, so we're sorting based on usage seconds. Next, let's write reverse equal true. Normally, Python sorts from smallest to largest, but we want the opposite. We want the highest usage time first, so reverse equal true flips the order. Now we need a place to build our display text, so we create a text variable and set it equal to empty quotes. Now this will create an empty string, and we'll gradually add information to it. Now let's loop through our applications. We'll write for app, sec in sorted apps and then pass :5. Notice the :5. This is called slicing. It means only use the first 5 items. So even if the user has 20 applications, we'll only display the top 5. That keeps everything clean and readable. Now inside the loop, we need to convert each application's seconds into hours, minutes, and seconds. So we'll repeat these same calculations we used earlier. Once we have those values, we can build a display line. So let's write text plus equal. Now the plus equal operator means take the existing text and add more onto it. Then we'll write fstring app : less than 25. The number 25 tells Python to reserve 25 characters for the application name. This helps keep everything aligned. And then we again use the fstring to display the formatted time. And the new line character moves the next application onto a new line. Now all that's left is displaying it. So let's write appbox.configure and then pass text equal text. This updates the usage panel with the formatted application list. And that's it. Every time the update dashboard runs, the dashboard automatically refreshes itself. The total time updates, the application rankings update, and the usage display updates, which means our interface is now directly connected to our tracking data. And that's a huge milestone, because for the first time in this project, users can actually watch their screen time data appear live on the dashboard. All right, let's run the application and see if everything we've built is finally working together. I'm going to click Start Tracking, and now I'm going to spend a few seconds moving between different applications, maybe Chrome, maybe VS Code, and after a few moments, look at what's happening on the dashboard. The total time section is increasing automatically, and underneath that, we can now see individual applications appearing inside the usage panel. As more time is spent inside an application, its usage value continues increasing. And because we're sorting everything by usage time, the most used applications automatically stay at the top. So up until now, our tracker has been collecting data behind the scenes, but now that information is finally visible. Users can actually see where their time is going in real time, and that's what turns this from a collection of Python functions into a real dashboard application. Now that we can collect, display, and save data, the next thing we'll add is a visual chart so users can understand their screen time at a glance.
All right, so our dashboard is now displaying usage information. Users can see their total track time, their most used applications, and live updates as tracking continues. But sometimes numbers alone aren't enough. A visual representation can often tell the story much faster. So let's build a chart feature. The idea is simple. When the user clicks the View Chart button, we'll generate a pie chart showing how screen time is distributed across applications. So let's start by creating the function. We will create a showChar function. This function will run whenever the user clicks the View Chart button. Now, before we create a chart, we need to think about something important. What happens if the user clicks the button before tracking anything? In that situation, we wouldn't have any data to display, and trying to generate a chart without data doesn't make much sense. So let's handle that situation first. We'll write if not usage data. Now, let's try to understand this first. Remember, usage data is our dictionary that stores tracked application information. If the dictionary is empty, Python treats it as false. And because we're using not, we're essentially asking, is the dictionary empty? If the answer is yes, then we need to warn the user. So we write messagebox.showWarning. Now remember earlier when we imported messagebox from Tkinter. This is exactly where we use it. The showWarning function displays a pop-up warning window. The first argument is the title of the pop-up. We'll write no data. And the second argument is the message. We'll write track some apps first. So if someone tries generating a chart without any tracking data, they'll see a helpful message instead of a broken feature. Now, after showing the warning, we don't want the rest of the function to continue running. So let's write return. Remember what return does. It immediately exits the function. So after the warning appears, Python stops executing anything else. Now, let's assume the user actually has tracking data. The next thing we need is a list of application names. So let's write apps equals list. And inside the list function, we pass usagedata.keys. Let's break this down. The keys method returns all the keys stored inside the dictionary. And remember, our keys are application names, something like chrome.exe, code.exe, and spotify.exe. The list function converts those keys into a list that matplotlib can use. Now let's create another list. We'll write seconds equals list and pass usagedata.values. This works exactly the same way, except this time we're retrieving the values. Those values represent usage time in seconds. So if our dictionary looked like this, then apps would contain chrome.exe and code.exe, and seconds would contain 120 and 60. Now let's create the chart window. We'll write plt.figure and set the fig size equal to 7,7. The figure function creates a new chart area, and fig size controls its size. The first number represents width, and the second number represents height. I'm choosing a square shape because pie charts generally look best when they're displayed inside a square area. Now it's time to create the actual chart, so let's write plt.pie. This function creates a pie chart. The first argument is seconds. These values determine the size of each slice. Applications with larger usage times receive larger portions of the chart. Next, we write labels equals apps. This tells matplotlib which label belongs to each slice. Without labels, we'd see colored slices but wouldn't know which application they represent.
And finally, we write AutoPCT. Now, this parameter controls how percentages are displayed. The 1.1f means show one decimal place. So instead of displaying 60, we'll see 60.0%. This makes the chart easier to read. Now let's give the chart a title. We'll write plt.title, and then we write the title. Titles are important because they provide context. The moment someone sees the chart, they immediately understand what it's showing. And finally, plt.show. This line tells Matplotlib to display the chart window. Without show, the chart would be created internally but never actually appear on the screen. And that's it. With just a few lines of code, we've transformed raw tracking data into a visual representation that users can understand instantly. Instead of reading through rows of numbers, we can immediately see which applications are consuming most of our time.
All right, let's see this feature in action. I'm going to start tracking for a few moments and spend some time switching between different applications. Maybe a little time in Chrome, a little time in VS Code, and then a little time somewhere else. Now that we have some tracking data, let's click View Chart. And there it is, a complete visual breakdown of our screen time. Notice how each slice represents an application, and the size of each slice corresponds to how much time was spent using that application. So instead of reading through rows of numbers, we can immediately understand where most of our time is going. And honestly, this is one of the biggest advantages of data visualization. The information already existed, but presenting it visually makes it much easier to understand. At this point, our application can collect data, display data, save data, and visualize data. There's only one major feature left, and that's exporting the data so users can save the results outside of the application. And that's exactly what we'll build next. All right, so we've reached the final major feature of our application, and that's exporting data. Because while dashboards and charts are great, users often want access to the raw data itself. Maybe they want to open it in Excel. Maybe they want to perform additional analysis, or maybe they simply want to keep a record of their screen time history. So let's create a feature that exports our tracking data into a CSV file. We'll start by creating a function. So we will create a function called export report. This function will run whenever the user clicks the Export CSV button. Now, before we try exporting anything, let's make sure we actually have data available, because if the user hasn't tracked any applications yet, there's nothing to export. So let's write, if not usage data. By now, this should look familiar. Remember, usage data is our dictionary containing application usage information. If it's empty, Python treats it as false. So we're essentially asking, do we have any tracking data? If the answer is no, we'll simply exit the function. So we'll simply return. Notice that we're not displaying a warning here, and that's okay. For this project, we're keeping things simple. If no data exists, we simply stop the export process. Now let's create a data frame. We'll write df equals pd.dataframe. A data frame is one of the most important structures in Pandas. You can think of it as a table, very similar to an Excel spreadsheet. Now inside the data frame, we need to define our columns. So we write application, usage data.keys, and seconds used, usage data.values. Let's understand what's happening here. The first column is called application, and the data for that column comes from usage data.keys. Remember, the keys in our dictionary are application names, things like chrome.exe, code.exe, spotify.exe. The second column is called seconds used, and its values come from usage data.values. These are the usage times associated with each application. Now that the data frame exists, we need a file name. So let's write file name equals fstring, and then we write screen report, then datetime.now.strftime.csv. Now, I know this looks complicated, but let's break it down. The first part, screen report, is simply a fixed name. Every exported file will start with those words. Then we're using datetime.now to retrieve the current date and time, and strftime to format it. This will give year, month, date, then hour, minutes, and finally seconds. This is actually a very useful technique because it guarantees every exported file gets a unique name. Without timestamps, exporting multiple reports could overwrite older files. Now let's save the file. We'll write df.tocsv.
This method converts the data frame into a CSV file. The first argument is file name, which tells pandas where the file should be saved. Then we'll write index equals false. Now let's talk about why this matters. By default, pandas includes row numbers from 0 along the left side. For this project, those numbers don't provide any useful information. So by setting index equals false, we prevent them from being included in the CSV file. The result is a cleaner report. Now the export itself is finished, but we should also let the user know that everything worked. So let's display a message box. So we'll write messagebox.showInfo. This creates an informational pop-up. The title will be export complete, and the message will be saved as file name. Notice the new line character. This creates a new line, so the pop-up displays nicely and clearly shows the generated file name. And that's it. With just a few lines of code, we've created a complete export system. Users can now take all of their tracking data and save it into a CSV file for future analysis. And that makes our application feel much more professional because the data isn't trapped inside the dashboard anymore. Users can actually use it elsewhere. Alright, so before we wrap up the project, I want to spend a few minutes improving the appearance of our interface. Because functionality is important, but presentation matters too. Think about the applications you use every day. Whether it's a website, a desktop application, or a mobile app, the visual design plays a huge role in the overall experience. So let's start by creating a color that we'll use across all of our buttons. I'm going to write primary equal orange color. Now notice that this variable name is written entirely in uppercase. This is a common Python convention. Whenever developers create values that are intended to remain constant throughout the program, they often use uppercase names. These are sometimes referred to as constants. Now, the value itself is a hexadecimal color code, and this particular color is a vibrant orange. Next, let's create another color. We'll write hover equal dark orange color. And the reason we're creating it is that we want the buttons to respond visually when the user moves their mouse over them. That effect is called the hover effect. Most modern applications use hover effects because they make interfaces feel more interactive and responsive. Now that we have our colors, we need a way to apply them to all of our buttons. And instead of configuring every button individually, we're going to use a loop. So let's write for btn in start btn, comma, stop btn, comma, chart btn, comma, export btn. Let's break this down. Inside the square brackets, we're creating a list, and that list contains references to all 4 of our buttons. Then we're using a for loop to go through them one at a time. During each iteration, the variable btn will refer to one button. For example, during first iteration, start btn. During the second iteration, stop btn. And during the third iteration, chart btn, and so on. This is much cleaner than writing the same configuration code 4 separate times. Now, inside the loop, let's write btn.configure. Remember, configure allows us to modify properties of an existing widget. The first property we're changing is FG_color and set it equal to primary. The FG_color controls the main button color, and because primary contains our orange color, all buttons will now use that orange theme. Next, let's write hover_color equal hover. This defines the color that appears when the user hovers over the button. Since hover is slightly darker, users will see a subtle visual change whenever they move their mouse over a button. This makes the interface feel much more polished. And finally, text color equal to white. This controls the color of the text displayed inside the buttons. And that's it. With just a few lines of code, we've given all 4 buttons a consistent visual style. They're now using the same color palette, the same hover behavior, and the same text color, which helps the entire dashboard feel much more cohesive and professional. All right, let's run the application one more time. Now, the functionality hasn't changed. All of our features still work exactly the same way. But notice how much cleaner the interface looks. All of the buttons now share the same color palette, and when I move my mouse over them, you can see the hover effect kick in. It's a small detail, but small details often make the biggest difference in user experience. This is one of those changes that doesn't add any new functionality, but it absolutely improves the overall feel of the application. And that's something worth paying attention to whenever you're building your own projects, because professional-looking projects are usually the result of many small improvements working together. All right, so after all that coding, it's finally time for the best part.
let's see everything working together. I'm going to run the completed application. And immediately you can see our dashboard appear. We have the title at the top, we have the status indicator, we have the session timer, we have our control buttons, and we have the dashboard area waiting to display tracking information. Now at the moment, nothing is being tracked yet. The status says ready, the timer still sitting at 0, and that's exactly what we expect. So let's start a tracking session. I'm going to click Start Tracking. Immediately, notice that the status changes to Tracking Running, and the timer begins counting upward. Now, while the tracker is running, let's actually use some applications. I'm going to switch over to Google Chrome for a few seconds. Then I'll come back to VS Code, then back to Chrome again. And while I'm doing that, our tracking system is continuously monitoring which application is currently active. Every second, it's collecting information and updating our usage data. Now, let's return to the dashboard. And look at what's happening. The total time section is increasing automatically. And underneath that, we can now see application names appearing inside the dashboard, something like chrome.exe and code.exe, along with the amount of time spent in each one. And because we're sorting everything by usage time, the applications receiving the most attention automatically appear near the top. This is really where the project starts to feel useful, because we're no longer just collecting information, we're actually displaying it in a way that's easy to understand. Now let's visualize the same data. I'm going to click View Chart. And there it is, a pie chart showing exactly how our screen time is distributed. Notice how each slice corresponds to one of the tracked applications. If more time was spent inside Chrome, Chrome receives a larger slice. If more time was spent inside VS Code, then VS Code receives a larger portion of the chart. This makes it incredibly easy to understand where your time is going without having to read through rows of numbers. Now let's close the chart and finish our tracking session. I'll click Stop Tracking, and the timer resets. The status changes to Stop Tracking, and behind the scenes, all of our collected information has been saved into the database. Now let's test the final feature. I'm going to click Export CSV. A confirmation message appears letting us know that the export was successful, and that also tells us the name of the file that was created. Now, if I open my project folder, you can see the CSV report sitting there. Let's open it. And inside, we can see the exact information collected during the session. Application names, usage times, everything neatly organized inside a spreadsheet format, which means we can now open it in Excel, import it into Power BI, perform further analysis, or simply keep it as a record of our screen time activity. Now, before we wrap up the project, there's one more interesting behavior that I want to show you. Earlier, we completed a tracking session, stopped tracking, and exported the results. But what happens if we start tracking again without closing the application? Let's test it. Notice that right now, the timer has been reset back to 0 because the previous session ended. Now I'm going to click Start Tracking one more time. And immediately you can see that the timer starts counting from 0 again. And that's exactly what we expect, because this timer represents the current tracking session. But now look closely at the dashboard. Notice something interesting. The usage statistics did not reset. You can still see entries like chrome.exe and python.exe, code.exe already present in the dashboard. And as I continue using the applications, those values keep increasing from where they previously stopped. The same thing happens with the total time section. Instead of going back to 0, it continues increasing from the previous value. So if the dashboard previously showed 10 minutes of tracked activity, it doesn't forget that information when a new session begins. It simply continues accumulating more usage data. And the reason this happens is because while we reset the session timer when a new tracking session starts, we never clear the usage data dictionary. That means the application continues building on the data that was already collected. Now, whether you consider this a feature or something you'd like to change depends on your own requirements. Some screen time trackers accumulate data across multiple sessions, while others completely reset everything whenever a new session starts. For this project, we've chosen to keep accumulating the usage information, so users can continue tracking without losing previously collected data. And personally, I think that's a pretty useful behavior, because it allows the dashboard to build a more complete picture of how the computer is being used over time. And that's it. We started this project with nothing more than an empty Python file. Then, step by step, we built a database, an application tracker, a background tracking engine, a live dashboard, data visualization, CSV exporting, and a modern graphical interface. And the best part is that every feature was built from scratch, using concepts that you can reuse in your own projects. If you followed along and built this project yourself, congratulations! You've done much more than just learn Python syntax. You've built a complete desktop application that combines databases, threading, GUI development, data visualization, file exporting, and a modern graphical interface. And honestly, that's one of the best ways to improve as a programmer. Don't just learn concepts, build things with them. If you enjoyed this project and want to see more beginner-friendly Python projects like this, make sure to subscribe to the channel and let me know what you'd like to build next. Thanks for watching, and I'll see you in the next video.